Hello friends, in our last discussion we talked about the transistor biasing circuits. DC biasing is used to establish fixed DC values for the transistor currents and voltages called the DC operating point or Q point. The things we learnt about biasing a transistor earlier will now be applied to bipolar junction transistor circuits, which are used as small signal amplifiers. The term small signal refers to the use of signals that take up a relatively small percentage of an amplifier's operational range. Additionally, you will learn how to reduce an amplifier to an equivalent DC and AC circuit for easier analysis, and you will learn about multi-stage amplifiers. Amplifier operation. The biasing of a transistor is purely a DC operation. The purpose of biasing is to establish a Q point about which variations in current and voltage can occur in response to an AC input signal. The applications where small signal voltages must be amplified, such as from an antenna or a microphone, variations about the Q point are relatively small. Amplifiers designed to handle these small AC signals are often referred to as small signal amplifiers. After completing this section, you should be able to describe amplifier operation, identify AC quantities, and discuss the operation of a linear amplifier. AC quantities. In the previous lecture, DC quantities were identified by non-italic uppercase subscripts such as IC, IE, VC and VCE. Lowercase italic subscripts are used to indicate AC quantities of RMS, peak and peak to peak currents and voltages. For example, IC, IE, IB, VC and VCE. Instantaneous quantities are represented by both lowercase letters and subscripts such as IC, IE, IB and VCE. Figure here illustrates these quantities for a specific voltage waveform. VCE can represent RMS, average, peak or peak to peak, but RMS will be assumed unless stated otherwise. VCE can be any instantaneous value on the curve. The linear amplifier. A linear amplifier provides amplification of a signal without any distortion, so that the output signal is an exact amplified replica of the input signal. A voltage divider biased transistor with a sinusoidal AC source capacitively coupled to the base through C1 and a load capacitively coupled to the collector through C2 is shown in figure here. The coupling capacitors block DC and thus prevent the internal source resistance Rs and the load resistance RL from changing the DC bias voltages at the base and collector. The capacitors ideally appear as shorts to the signal voltage. The sinusoidal source voltage causes the base voltage to vary sinusoidally above and below its DC bias level VBQ. The resulting variation in base current produces a larger variation in collector current because of the current gain of the transistor. As the sinusoidal collector current increases, the collector voltage decreases. The collector current varies above and below its Q point value ICQ in phase with the base current. The sinusoidal collector to emitter voltage varies above and below its Q point value VCEQ, out of phase with the base voltage. A transistor always produces a phase inversion between the base voltage and the collector voltage. The operation just described can be illustrated graphically on the AC load line as shown in figure. The sinusoidal voltage at the base produces a base current that varies above and below the Q point on the AC load line as shown by the arrows. Lines projected from the peaks of the base current across to the IC axis and down to the VCE axis indicate the peak to peak variation of the collector current and collector to emitter voltage as shown. Transistor AC models. To visualize the operation of a transistor in an amplifier circuit, it is often useful to represent the device by a model circuit. A transistor model circuit uses various internal transistor parameters to represent its operation. Transistor models are described in this section based on resistance or R parameters. Another system of parameters called H parameters is also discussed briefly. After completing this section, you should be able to list and define the R parameters, describe the R parameter transistor model, compare AC beta and DC beta, and finally, will be able to define and list the H parameters. R parameters. The 5 R parameters commonly used for BJTs are given in table here. The italic lowercase letter r with a prime denotes resistance internal to the transistor. R parameter transistor model. An R parameter model for a BJT is shown in part A of the figure. For most general analysis work, it can be simplified as follows. The effect of the AC base resistance RB is usually small enough to neglect, so it can be replaced by a short. The AC collector resistance RC is usually several hundred kilo ohms and can be replaced by an open. The resulting simplified R parameter equivalent circuit is shown in part B of the figure. Now, we shall interpret this model circuit in terms of a transistor's AC operation. A resistance R E appears between the emitter and base terminals. This is the resistance seen looking into the emitter of a forward biased transistor. The collector effectively acts as a dependent current source of alpha AC into IB or equivalently beta AC into IB, represented by the diamond shaped symbol. These factors are shown with a transistor symbol in this figure. For amplifier analysis, the AC emitter resistance RE is the most important of the R parameters. To calculate the approximate value of RE, you can use this equation here. This equation is derived assuming an abrupt junction between the N and P regions. It is also temperature dependent and is based on an ambient temperature of 20 degrees Celsius. The numerator will be slightly larger for higher temperatures or transistors with a gradual instead of an abrupt junction. Although these cases will yield slightly different results, most designs are not critically dependent on the value of RE, and you will generally obtain excellent agreement with actual circuits using the equation as given here. Comparison of the AC beta to the DC beta. For a typical transistor, a graph of IC versus IB is nonlinear as shown in part A of figure. If you pick a Q point on the curve and cause the base current to vary an amount delta IB, then the collector current will vary an amount delta IC as shown in part B. At different points on the nonlinear curve, the ratio delta IC over delta IB will be different, and it may also differ from IB over IC ratio at the Q point. Since beta DC is equal to IC over IB and beta AC is equal to delta IC over delta IB, the values of these two quantities can differ slightly. H parameters. A manufacturer's data sheet typically specifies H or hybrid parameters like HI, HR, HF, HO because they are relatively easy to measure. The four basic AC H parameters and their descriptions are given in table here. Each of the four H parameters carries a second subscript letter to designate the common emitter, common base or common collector amplifier configuration as listed in this table. The term common refers to one of the three terminals E, B or C that are referenced to AC ground for both input and output signals. The common emitter amplifier. As you have learned, a BJT can be represented in an AC model circuit. Three amplifier configurations are the common emitter, the common base and the common collector. The common emitter configuration has the emitter as the common terminal or ground to an AC signal. CE amplifier exhibit high voltage gain and high current gain. Figure here shows a common emitter amplifier with voltage divider bias and coupling capacitors C1 and C3 on the input and output and a bypass capacitor C2 from emitter to ground. The input signal V in is capacitively coupled to the base terminal. The output signal V out is capacitively coupled from the collector to the load. The amplified output is 180 degrees out of phase with the input. Because the AC signal is applied to the base terminal as the input and taken from the collector terminal as the output, the emitter is common to both the input and output signals. There is no signal at the emitter because the bypass capacitor effectively shorts the emitter to ground at the signal frequency. All amplifiers have a combination of both AC and DC operation, which must be considered, but keep in mind that the common emitter designation refers to the AC operation. Phase inversion. The output signal is out of phase with the input signal. As the input signal voltage changes, it causes the AC base current to change, resulting in a change in the collector current from its Q point value. If the base current increases, the collector current increases above its Q point value, causing an increase in the voltage drop across RC. This increase in the voltage across RC means that the voltage at the collector decreases from its Q point. So, any change in the input signal voltage results in an opposite change in collector signal voltage, which is a phase inversion. DC analysis. To analyze a common emitter amplifier as discussed earlier and shown here again in figure, the DC bias value must first be determined. To do this, a DC equivalent circuit is developed by removing the coupling and bypass capacitors, because they appear as far as the DC bias is connected. This also removes the load resistor and signal source. The DC equivalent circuit is shown in figure here. Thevenizing the bias circuit and applying Kirchhoff's voltage law to the base emitter circuit, we are to find out the values of various voltages, current and resistance. As shown here, RTH is equal to R1 into R2 over R1 plus R2. Substituting the values given in the circuit, we get RTH equal to 5.19 kilo ohms. Similarly, VTH is equal to R2 over R1 plus R2 into VCC. Substituting the values, we get VTH is equal to 2.83 volts. IE is equal to VTH minus VBE over RE plus RTH over beta DC, and IE comes out to be 3.58 milliamperes. As IC is approximately equal to IE, we get IE equal to 3.58 milliamperes, and VE is equal to IERE and comes out to be 2 volts. VB comes out to be 2.7 volts, and VC is equal to VCC minus ICRC and is equal to 8.42 volts. VCE is equal to VC minus VE and is equal to 6.42 volts. AC analysis. To analyze the AC signal operation of a common emitter amplifier discussed earlier and shown here is developed into an AC equivalent circuit by replacing the capacitors C1, C2 and C3 by effective shorts, because their values are selected so that Xc is negligible at the signal frequency and can be considered to be 0 ohm, and also the DC source is replaced by ground. A DC voltage source has an internal resistance of near 0 ohm because it holds a constant voltage independent of the load. No AC voltage can be developed across it, so it appears as an AC short. This is why a DC source is called an AC ground. The AC equivalent circuit for the common emitter amplifier is shown in figure here. Notice that both RC and R1 have one end connected to AC ground, because in the actual circuit they are connected to VCC, which is in effect AC ground. In AC analysis, the AC ground and the actual ground are treated as the same point electrically. Signal voltage at the base. An AC voltage source Vs is shown connected to the input in figure here. If the internal resistance of the AC source is 0 ohm, then all of the source voltage appears at the base terminal. If, however, the AC source has a non-zero internal resistance, then 3 factors must be taken into account in determining the actual signal voltage at the base. These are the source resistance Rs, the bias resistance and the AC input resistance at the base of the transistor Rn base. This is illustrated in the part A of the figure shown and is simplified by combining R1, R2 and Rn base in parallel to get the total input resistance Rn total, which is the resistance seen by an AC source connected to the input as shown in part B of figure. A high value of input resistance is desirable so that the amplifier will not excessively load the signal source. This is opposite to the requirement for a stable Q point, which requires smaller resistors. The conflicting requirement for high input resistance and stable biasing is but one of the many trade-offs that must be considered when choosing components for a circuit. As you can see in the figure, the source voltage Vs is divided by Rs, the source resistance, and Rn total, so that the signal voltage at the base of the transistor is found by the voltage divider formula as shown here. If Rs is equal to Rn total, then Vb is approximately equal to Vs, where Vb is the input voltage Vn to the amplifier. Input resistance at the base. To develop an expression for the AC input resistance looking in at the base, use the simplified R parameter model of the transistor. Figure here shows the transistor model connected to the external collector resistor Rc. The input resistance looking in at the base is given by this equation. Rn base is equal to Vn over In and is also equal to Vb over Ib. The base voltage is Vb is equal to Ie into Re, and since Ie is approximately equal to Ic, Ib is equal to Ie over beta Ac. Substituting for Vb and Ib, Rn base is equal to Vb over Ib and is equal to Ie Re over Ie oblique beta Ac. Cancelling Ie, Rn base becomes equal to beta Ac into Re. So, friends, here we come to the end of our discussion and therefore, we sum up. In this lecture, we have discussed transistor models, defined the R and H parameters, described the R parameter transistor model, compared AC beta and DC beta, and in the case of common emitter amplifier, we described and analyzed the operation of common emitter amplifiers, discussed a common emitter amplifier with voltage divider bias, discussed phase inversion, performed DC and AC analysis, and finally, represented the amplifier by its DC and AC equivalent circuits. In the next lecture, we shall be discussing the common collector and common base amplifiers. See you in the next lecture. Thank you very much.